What do you mean not live? What does that mean?
We're live now.
I'm typing in the questions that are not live.
Okay, we are ready?
It's live.
Good morning, everyone. Thank you so much for joining us. And we are excited to have you here this morning. This is the first live session that we are running after the start of our new astrobiology course. So I'm going to let Chris tell you a little bit about that. If you don't know about the astrobiology course, you should head over and sign up right now if you are here from the astrobiology course. Thank you so much for joining us. We are excited to be here this morning.
Yes, welcome everyone from London again, where we'll be, or I'll be, for another couple of months until the end of June. There's a lot of work to put it together. We're very excited to have launched our astrobiology course on Coursera. So we're now running 3 MOOCs in parallel, and the astrobiology one is exciting because obviously search for life in the universe and exoplanets are just about the hottest fields in astronomy right now. So there's a lot going on there. And it's probably not escaped people's attention that last week was a pretty big news week in the arena of black holes, and I expect we'll be getting a few questions on that. And it is, in fact, purely coincidence that although I'm in the UK, we're also competing with a certain, newsworthy political event that's happening at this moment. So I appreciate you prioritizing astronomy over politics. Ready for your questions?
Excellent. All right. So the first question is actually from Cecil Hansen, who emailed a question in. And it's, I was taught that black holes consume all matter from both their front and rear openings. Quite understandable, but what I do not understand is exactly how scientists determine which is the front and which is the back opening. Can you shed some light on these ideas, Chris?
Right. Well, I guess the first thing to say is that in the standard explanation of black holes, they don't have a rear opening. The front and rear opening analogies are sort of animalistic and they're very evocative, but they're probably not accurate. Black holes are tombs of matter and radiation. They're places where nothing can get out, regions of space-time pinched off, if you like, from the rest of the universe. And in standard and basic black hole theory, there is no exit. So there's no rear opening. There's just the way in, which is through the event horizon. Now, it is possible in principle and in theory that if you have complex shaped space-times, convoluted in 3 or more dimensions, you could possibly have an exit point in another part of the universe. That's the idea of a black hole as a portal in space, or a white hole at the other end where the stuff that went into the black hole eventually comes out as radiation, probably. That is purely hypothetical. So just to keep it straight up in terms of black hole theory, they're just tombs of matter and radiation with no exit. Ready for the next question?
All right, and then I think I just want to let everybody know that we're today for the chat, because of the recent announcement, we're probably going to prioritize black hole and black hole related questions, at least for the first half of this live session. So if we skip over your question, make sure you come back next time and ask it, or we'll hopefully get to it in the second half. But there's a lot of excitement around the recent announcement. So the next question is from A. Richter, who's on with us live, who asks, is there a proportional relationship between the mass of a central black hole and the mass of its host galaxy? If so, what is that relationship, and why does it exist, and why does it apply to all galaxies?
That's a very good question, and there's a lot of research on that subject. This research became possible when we were able to determine and isolate and measure the mass of black holes in nearby galaxies, which started with the Hubble Space Telescope. We're looking for high-velocity stars in the center parts of galaxies driven by a dark object. So it really wasn't until the 1980s and into the 90s that we had enough data to look at any kind of correlation between central black hole mass and the galaxy that contains it. The best correlation that people have been able to find is not actually between the black hole mass and the entire galaxy mass. It's between the black hole mass and the bulge mass, or equivalently, the mass of old stars in the galaxy. Now, viewed in these terms, the Milky Way, as a mid-type spiral galaxy, has a rather modest bulge in the center of the galaxy, a few thousand light years across, where the old stars live. There are late-type spirals which have even smaller bulges, And there are early type spirals which have large bulges, and elliptical galaxies are essentially all bulged because all of their stars are old. So if you think of those parts of a galaxy of any type, then the black hole correlates very well, the mass linearly, with the mass of the old stars in the galaxy over about 5 orders of magnitude, which is quite remarkable, from about 1,000,000 solar masses down up to about 10 billion solar masses, the most massive black holes we know of. So that correlation is pretty clear. It's pretty robust. It's been studied in many ways, sample sizes of 50 or 100, maybe more data points. The question of why is not yet fully explained. It is intuitively clear that if black holes form in the center of galaxies and black holes and galaxies rather grow by mergers and acquisitions in a hierarchical way as the universe evolves, then it's fair enough that as galaxies merge, the black holes they contain will merge and their masses add together. So black holes and galaxies should grow together in a certain general sense. That's still not quite enough to explain the tightness of this correlation. So astronomers consider that there is still some interesting astrophysics there. And to put all this in context, in this scaling relation, the black hole mass is less than 1%. It's about 0.1% of the entire mass of the galaxy. So the black holes are really very small mass components of any galaxy, including the Milky Way. Ready for the next question?
All right, Chris, the next question is related again to the recent discovery, the recent release of the image of a black hole, and it is regarding the algorithm used to merge all the data from the black hole. Will this technology enable more astronomy of distant objects? And then also related, does it really have the angular resolution of a telescope the size of the Earth, and how is that possible?
Yes, the data techniques which have been getting some appropriate attention, I think, because these people who work on these algorithms are sort of unsung heroes of a project like the Event Horizon Telescope. These are very sophisticated methods for combining radiation from distant and separate telescopes. The basic techniques of interferometry have, however, been around for over half a century. Radio astronomy started doing interferometry that long ago. Obviously, computers have advanced substantially in that time, and so the Event Horizon Telescope was really taking data very rapidly, trying to use every tiny bit of information taken by any of the telescopes and optimally combine it in a way that suppressed noise as well as possible. And doing all that is computationally very intensive, and that's why it sucked up a lot of computer power. So this method, however, of combining information from different telescopes, like I said, it's half a century old. It depends on the fact that when two telescopes at a separate location, observing at the same wavelength with hopefully identical receivers, and so detecting the radiation in the same way, if the detection of the radiation is time tagged with a molecular clock or an atomic clock, so extremely accurate noting of the time of arrival, and then that radiation is combined where the phase information, the phase of the electromagnetic radiation received by each telescope is preserved, then you can combine radiation from separate points as if these points were part of some very large radio dish, in principle as big as the Earth itself. So that's the sort of basic principle. You're essentially acting by preserving the phase information and the arrival time information. You're reconstructing a situation as if each of the radio telescopes scattered around the surface of the planet were part of some huge radio dish. And the angular resolution is given by the size of the dish. And the size of the dish, in this case, is the size of the Earth. So obviously, you have a huge sized dish and a very, very low angular resolution, thousands or tens or hundreds of thousands of times better than a single radio telescope. Now, of course, you don't have the collecting area of a dish the size of the Earth because you're still just combining the information from a dozen or so fairly small radio dishes. But in this case, the sensitivity is not the biggest issue. There's a fair amount of radiation coming from M87 or the galactic center to do these experiments. The information that's difficult to get and valuable to get is the timing and phase information that lets you reconstruct the image as if you had a huge radio telescope. Ready for the next question?
The next question is from Ravi, who sent a question via email, who asks, the EHT team used millimeter waves to image the black hole at M47. What is the source of these wavelengths?
The source of radiation from any galaxy, the center of any galaxy, and millimeter wavelengths is essentially hot gas. So this is thermal radiation, basically the same kind of thing that happens when any gas glows. The gas in the center of these galaxies that's not very close to the black hole. The gas very close to the black hole would be heated to millions of Kelvin, and so that would glow in blue optical, ultraviolet, or even soft X-rays. So significantly further out from the black hole, which is where the gas is that in the M87 case is backlighting the event horizon, and the same will be true in the galactic center case when they publish that. This gas is substantially cooler. It may only be thousands or hundreds of Kelvin. And gas at that temperature will radiate in the infrared extending to the short radio wavelengths. So millimeter is a short radio wavelength, the kind of radio waves your radio might work with, or centimeter waves, or even longer. So that's where the radiation comes from. It's from the hot gas. And millimeter waves are a sort of compromise between radiation that's long enough wavelength that it can escape the center of a galaxy without obscuration, and also waves that are short enough that you can have very accurate imaging, because the resolution depends on the wavelength as well. Ready for the next question?
All right, the next question is from one of our, is also from email, and it is, what is the difference between a stellar black hole and a supermassive black hole apart from their masses?
Not much, actually. I mean, black holes are very singular and essentially simple objects. In the classic theory of black holes, they really only have three properties. They have mass, they have size, which is given by the event horizon, and the mass is the mass within the event horizon. And since they form from objects that had some degree of rotation or angular momentum, they have angular momentum too. Black holes are almost always spinning, based on a normal astrophysical situation. And those three properties are shared by all black holes, from the small ones that are left behind when massive star dies, to the huge ones that form sequentially by mergers of black holes and then accretion of matter in the centers of galaxies. Remember, the galaxies also have rotation. So the material that falls into and makes these big black holes grow will be feeding a situation where the massive black hole is spinning as well. So those are the three simple properties of black holes. The other property they share, according to Stephen Hawking's ideas, of course, is a property of temperature, thermal temperature, and the radiation that's emitted based on an incredibly small temperature, tiny, tiny fractions of a degree Kelvin, is called Hawking radiation. Ready for the next question?
All right, the next question is from Vince, who is on with us live, who asks, do black holes generate gravity waves?
Definitely. So gravity waves, or gravitational waves, or gravitational radiation, to use all the different ways people talk about this, essentially arise from any situation where mass configurations are changing, where mass is changing in some way. If you have a purely static situation, then you won't have gravity waves. But of course, in astrophysics, almost everything is changing. So an object, a black hole that's accreting, will emit gravity waves. A black hole that's spinning will emit a certain amount of gravitational radiation just from its spin. And then the more dramatic situations that LIGO observed, like black holes colliding and merging, will of course release the most intense form of gravitational radiation, the kind that was discovered just 3 or 4 years ago. So, but this is not just black holes. All masses, in theory, in Einstein's theory of general relativity, when they're changing their configuration, will emit gravitational radiation. So there are much more subtle and weak forms of gravitational radiation coursing through the universe from all of the situations where mass is changing or mass configurations are changing. It's just that our abilities with instruments are such that we can only detect the most dramatic types of gravity waves, and those are the ones that come from the most compact gravity objects and the most intense gravity objects, black holes or neutron stars. Ready for the next question?
All right. The next question is from Yassi, who is on with us live, who asks, excuse me, What does the picture of the black hole mean? How would we interpret it, the one that was seen in the media? Because it just looks like a black circle and is not really very distinct. So what are we seeing there?
Well, obviously, the striking thing about the discovery is the image itself, because we've never had a picture of a black hole of any kind. So it's a unique and unprecedented observation. That said, yes, if for people who are used to the ultra sharp imaging of planets and moons and galaxies based on Hubble Space Telescope, it's a little disappointing. It's a fuzzy blob. It's obviously radio waves, so you can't see it. It's just used, a color table is used to turn radio intensity into color, and by tradition, radio astronomers and X-ray astronomers tend to use an orange color scale. The size of the object is visible, so you're actually you're measuring the event horizon size directly. You're also able to see if it's oblate or prolate, which is to say whether it's squashed or not. And in situations of extreme angular momentum, it would have deviations from circularity. Also, in some of the more subtle effects of general relativity, it might have deviations from circularity. The illumination, the backlighting of the black hole is, as everyone had noticed, not symmetric. And that means that even if this black hole is sitting in a uniform disk of material, the distortions that we see in the radiation as it's backlighting represent a large amount of bending of that radiation by gravity. So the actual shape, the distortion, and the way it departs from symmetry is telling us about gravitational lensing. And so that's another affirmation of Einstein's theory in the field, in the regime of strong gravity, where we haven't tested it before. Now, in more detail, when the image gets sharper, they're obviously going to get more data, try and get the image sharper still. They will be starting to look for quite subtle signatures of black hole physics near the event horizon at the innermost radii of the gas that is behind the black hole and in front of the black hole. The observations are not at that level yet. So given how limiting this observation was, what can be learned is actually still quite impressive. Ready for the next question.
All right, the next question is from Eric, who's on with us live, who asks, is a black hole at the center of a galaxy driving the rotation of a galaxy?
And actually, it's responding to the rotation of a galaxy. Since the black hole forms in a galaxy, now whether there's a chicken and egg issue, so there is still an open research question as to whether in the early universe, which is to say the first 500 million years after the Big Bang, the seed black holes, probably of 100 or a few hundred times the mass of the sun, formed first, or the smallest pieces of dwarf galaxies formed first, and then black holes formed within them. That issue aside, generally, as I mentioned, galaxies are dominated by the mass of stars and dark matter. The black holes within them at every stage of their lives are a tiny fraction of their total mass. The material that forms the black hole and then causes it to grow over cosmic time comes from the galaxy itself. It comes from gas in the galaxy, or gas that falls into the galaxy, or gas lost from stars in the galaxy. So in all of those senses, the black hole is growing from material of the galaxy, and so is responding to the galaxy itself, to its gas supply, its angular momentum, the rate at which material falls into the center, and so on. So the black hole is really a measure of things that have happened in the galaxy rather than the other way around. Ready for the next question?
All right, our next question is from Benji Bear, who's on with us live, who asks, do black holes have charge?
That's an interesting question and is unresolved observationally. In the simplest versions of the black hole theory, no, they don't have charge. For the simple reason that the universe as a whole is electrically neutral. There's no large region of space we've ever seen or could see where charge is segregated, and so we have net electric charge in the universe. There are many parts of the universe where normal atoms, which is to say neutral atoms, do not exist, and the electrons are stripped off from the protons, remembering that most of the universe is hydrogen, or the electrons are stripped off the helium nuclei. That accounts for most of the universe, those two situations. But even if that is true, they are still mixed in the same region of space. So if you draw a circle or sphere around any region of space, it will be electrically neutral. We believe the same is true of black holes because, again, the material the black holes are made of is on average going to be electrically neutral. So there's no sensible way in which black holes could build up electric charge. Now, people have speculated, and this is pure speculation, that somehow inside the event horizon, segregation of charged matter may happen in a sort of a dynamo effect in the spinning black hole, and that could potentially charge up the event horizon. That is a completely uncorroborated speculation, and it actually deviates from part of our understanding of general relativity. So the simple answer to the question is no, we don't think black holes are charged. Ready for the next question?
All right, the next question is from Anders Nordqvist, who is on with us live, who asks, are black holes leaking Hawking radiation? I have heard that they are so cold that they will not leak until space is colder, and that won't happen for a long time. What's the real answer?
Yes, Hawking radiation is extremely subtle. Remember, the Hawking radiation results from the really quite rare and special circumstance of virtual pairs of particles and antiparticles, something that we know happens in the lab, and it gives the pure vacuum of space some small amount of energy. When that process happens near the event horizon, there's a finite chance that one member of the pair will leave and the other will escape. And the aggregate of that process is that a black hole will either leak radiation or mass. In other words, that it will radiate and equivalently evaporate. But when you plug in the numbers for a black hole that's left behind after a massive star dies, the Hawking radiation temperature is less than a billionth of a Kelvin, incredibly small. There's no way in astronomy we've ever been able to measure temperatures that small. The smallest temperature we've measured routinely, of course, is the microwave background at a level of 2.7 Kelvin. So nobody knows of a way of detecting the temperature of a black hole, especially since they're surrounded by extremely hot, messy gas. That tiny little radiation signal is dwarfed and buried in a much, much stronger radiation signal of accretion. And then the radiation is equally difficult, the Hawking evaporation or loss of mass is equally difficult to measure because the rate of evaporation is so slow, which is corresponding to saying that the radiation is very feeble. And so the evaporation time for a black hole that's left behind when a massive star dies is about 10 to the power 68 years. That is an incredibly long time, given the universe at the moment is only 10 to the 10 years old in round numbers. So that's trillions and trillions and trillions and trillions of times longer than the age of the universe up to this point. So there's no conceivable way we can measure such a feeble amount of mass loss from a black hole. It's hard enough to measure their mass in the first place, just with an accuracy of maybe 30%. So unfortunately, these two key predictions of Stephen Hawking are really, really far from being tested. They may never actually be testable. Ready for the next question?
All right, thank you, Chris. The next question is from Ryan Weber, who is on with us live, who asks, why do we see the bulges of galaxies populated with old stars as opposed to being distributed uniformly throughout the galaxy? Do stars that live long migrate inward gradually?
That's a good question, and we don't know all the answers to these questions about why galaxies have the shapes and morphologies they do. We see a set of galaxy shapes and morphologies. These were classified by Hubble early on when he was doing his observations in the 1920s and 30s, and they led to something that's been called the Hubble tuning fork diagram, where he put the morphologies of spiral and elliptical galaxies into a tuning fork shape and speculated that one type might evolve into another. It now seems clear that the different galaxy types, in particular spirals and ellipticals, are down to initial conditions and not they're not a situation where things can evolve into another. There are some exceptions to that. It is true that elliptical galaxies could have formed from a series of mergers that included smaller spiral galaxies. So giant elliptical galaxies may be situations where they got that way, and the old stars got essentially heated up and distributed into a spherical situation by a series of collisions and mergers over cosmic time. So in one sense, the shape of the old stars in space in a galaxy, usually a spheroidal distribution, not completely spherical, but close to it with some small amount of spin, is a reflection of the state of those stars when they formed. It's a sort of relic of the formation of the galaxy. And since those are the oldest stars in any galaxy, spiral or elliptical, they're sort of frozen relic of the formation situation of the galaxy. The spiral parts of galaxies, which also can include old stars in the bulge, are believed to have resulted more recently in the merger and process of mergers of smaller galaxies and the gradual infall of gas from the intergalactic medium. That gas in a rotating system will naturally end up in a disk, and the disk gets stirred up and spiral arms form and stars form. And so many of the disks of spiral galaxies are made of younger stars. They're made of material that's fallen in more recently than the galaxy formed, throughout its history, in fact. And so that presents a chronology of subsequent evolution of the galaxy rather than its initial conditions. So broadly speaking, that's the difference between the spiral components of a galaxy and the spheroidal or elliptical type components of a galaxy. Ready for the next question?
All right, so we've spent quite a bit of time on black holes and galaxies, so I want to give other questions an opportunity, and especially about astrobiology, since that is our latest course on Coursera. So the next question is going to be from Christopher Lyons, who is on with us live, who asks, do you believe that life is common throughout the galaxy? I know it seems inevitable given the statistical odds with billions of galaxies and billions of stars and countless planets, but what do you think?
Well, like most of my colleagues, I believe the odds that the galaxy, just take the Milky Way for our first instance and assume it's typical of all galaxies, the odds that the Milky Way is sterile, except for the Earth in terms of biology of any kind, they have to be pretty low at this point. So having confirmed over 4,000 exoplanets and having now found at least 300, closer to 400 Earth-like planets, that is, planets within a factor of 2 of the Earth in size or mass, and some substantial fraction of those 400 that are in the habitable zone of their parent stars, we already can project a very large number of habitable planets in the Milky Way. It's of order 10 billion. And so you're asking whether or not all those 10 billion exoplanets that are Earth-like at some level and are made of similar materials. The chemistry of the universe is universal. Water is not a rare ingredient in the universe, neither is carbon, the two base ingredients for life on Earth. So it does seem very unlikely that all of those situations are sterile and none of them led to biology. There's also a lot of time involved. You could have an Earth-like planet, that is to say a clone of the Earth, that formed 4, 5, maybe 6 billion years before the Earth and the solar system formed, and so has a head start on us in terms of biology. So even if it takes a while for the simple ingredients on a planet to get together, become more complex through natural processes, and form the rudiments of biology, there's plenty of time for it to happen. And that's why, in a nutshell, most astronomers and really most astrobiologists are confident that life exists elsewhere. However, that's just a plausibility argument. In science, you have to do better than that. And if it's entirely possible that it was a fluke. You could equally well and strongly argue that life on Earth was a fluke and support that with various arguments. Until we have evidence, we simply won't be able to say. Ready for the next question?
All right, our next question is from Jacob Olson, who asks, can we expect any mission to Europa in the next 10 or 20 years?
Yes, NASA and the Europeans, the European Space Agency, have had Europa missions on the table for a number of years now. Obviously, Europa is a compelling target in the outer solar system. It's a moon, a Galilean moon of Jupiter with a frozen ice crust of some kilometers thick that overlies a tens of kilometer deep water ocean. Not directly observed, but very confidently measured by our space probes from the 70s and 80s that orbited the moon and orbited Jupiter. So it really is a very high priority to go back and find out more about this system. For a while, NASA seemed to be heading for a quite ambitious Europa Explorer, Europa Clipper mission, which might include a lander and might include life detection instruments designed to dig into the ice a bit and possibly try and look for frozen bacteria or microbes in the ice. They've backed off the lander concept at the moment, or after putting it together in terms of proof of concept, they backed off of it. And now the current plan is to have an orbiter, which will make very detailed observations. Remember, this is decades after the first observations, so the instrumentation is far superior now. And this orbiter will have one of these splashdown objects, a massive ball or sphere that will splash into the ice and knock off some of the material and then sniff it with spectrometers as it continues to orbit and look for organic material or potentially life-bearing material. So that mission is on the table. NASA's budget woes and its capped budget threaten to be reduced next year in the president's budget, and we don't know. If NASA are lucky, they'll probably have the same budget as last year. It is really keeping this on a slow timeline. It's a decade off at least. And the travel time, remember, is another 5 years. So we're talking 16 or 17 years before this mission gets there. Very frustrating to some people, and some people think it's overly timid. There are continuous calls to have something more ambitious that would find the thinnest part of the ice crust, which might only be maybe 100 or 50 meters thick if you were lucky at some place where there's a fissure, and actually use a thermal plant to melt through the ice and release a hydrobot to actually look for life in the European Ocean. That's just not on the drawing board right now. It will be expensive, and so the mission that's being planned is very interesting, but not quite as exciting as the one we might conceive of. Ready for the next question?
All right, the next question is from Eric Nicholson, who's on with us live, who asks, have amino acids been found in any or many meteorites?
Yes, amino acids have been found in, I think, over a dozen meteorites now. The granddaddy of these detections was the Murchison meteorite, which astronomers learned disproportionate amounts from very particular meteorites, given the meteorites are falling on the Earth all the time. I mean, there's a rain of interstellar and interplanetary material that's thousands of tons a year that falls on the Earth. It's just very hard to identify it. And the bigger chunks, when they're screaming through the atmosphere, lighting it up, falling in remote places and discovered quickly, are disproportionately important. So the Murchison meteorite, which I can't remember exactly when it fell, I think back in the 70s, fell in Western Australia and was seen and recovered very, very quickly within a couple of hours. And that's key, because as soon as a meteorite lands and falls, it starts being contaminated with terrestrial material. So that meteorite was quickly taken into the lab, into a clean room, a secure room, and divided up, sent to different research groups. And I think within that meteorite, several dozen amino acids were found, including some that are part of terrestrial toolkit of life, the 20 or so amino acids that terrestrial life is based on, and some that are not. Remember that in terms of the definition of amino acids, chemically, the possible number, the hypothetical number of amino acids is about 100,000. And life on Earth has selectively used in its energy and information mechanisms just a couple of dozen of those. So it's not a ridiculous situation to find amino acids, some of which are terrestrial life-based and some of which are not terrestrial life-based. Also, equal amounts of left and right-handed molecules often have a handedness or a helicity, were found in the Murchison meteorite. That's not true of life. Life is preferentially used one-handedness of molecules for energy efficiency reasons. But the Murchison meteorite is not the only one, it's just the most prominent one. And I think now there are a number of cases where amino acids have been found. People then wonder, has anything more complex been found? Remember, the simplest amino acids in the backbone of life are only based on a couple of dozen atoms. So they're very simple molecules, really. Has any more complex molecule been found in meteorites? Some hydrocarbons with more than a few dozen atoms, but nothing that is so pivotal to the mechanism of life that it would warrant a news headline. But this is still active research, and we're always hoping for the next meteorite that is well enough preserved that we can look for more of these materials. Ready for the next question.
Thank you, Chris. The next question is from Shoshin, who's on with us live, who asks, what would happen to life on the Earth or the Earth if we lost our moon and or if we stopped having tides?
It's a very interesting hypothetical question. It's not going to happen. The tidal coupling of the moon and the Earth actually does mean that the Earth is getting away from us, if you like. It's receding at, I think, a few centimeters, maybe it's 4 centimeters a year. It's a not trivial amount, but obviously in astronomical terms, it's tiny. So that's based on the tidal interaction and the transfer of energy and angular momentum between the moon and the Earth. And if you play that forward, there probably is a time in the far future, by which I mean billions of years, when the moon will no longer be tidally locked to the Earth. And that's an interesting thing. Obviously, its tidal effect on the Earth will diminish as it recedes from the Earth, and at some point it probably will, in fact, be lost into the solar system. But this is all very, very far away. But if we just imagine, hypothetically, the moon suddenly just disappearing, not being there, what effect would it have on the Earth? Well, yes, it would obviously mean the Earth would no longer have any tides. And the tides are actually important. They're important in the biosphere in a number of ways. They obviously act to charge and recharge coastal regions. There are intertidal zones, for example, which are extremely rich in sea life. And those intertidal zones would simply not function the way they do now if tides didn't exist. So there's a sort of cleansing and cycling mechanism associated with tides that is very useful for life on Earth. I don't know that humans would be that perturbed. Obviously, surfing would be more difficult, and various things that we like to do would be not possible. So those would be the biggest effects. The long-term effect, of course, is that the moon tidally locking to the Earth stabilizes the Earth's spin axis. Mars, a smaller but similar type terrestrial planet, which has an orbital tilt, that tilt varies over time between about 20 and 45 degrees. The Earth's orbital tilt has been fairly locked at 23.5 degrees because of the presence of the moon. So without the moon, the Earth's seasons over long time scales would start to change because our orbital tilt would drift to possibly lower and possibly larger numbers. So seasons might go away or they might get more extreme. But again, these would be very long time scale effects. But it's definitely an interesting hypothetical to consider. Ready for the next question?
Okay, the next question from one of our live viewers is from Omri Baron, who asks, where is E.T. and is she shy?
She may well be shy, and it's in the he, she, or it. I don't really know where you can place your bet, and probably the safest bet is to say it rather than he or she. Gender is a particular thing to terrestrial life, and not even all forms of terrestrial life, just advanced multicellular life. So does ET have a gender? Probably not. Where is ET? Probably out there, but maybe not. The question of life anywhere at the microbial level is easier to be confident that there is life there because of the number of habitable places with all the ingredients for microbial life and the rapidity with which the first life formed on Earth. The life evidence on Earth goes back pretty securely to 3.8 billion years ago, and with more uncertainty to 4 and maybe 4.1 billion years ago, when the Earth was very different and pretty uninhabitable place to our view. So life formed very quickly in that simple microbial sense. Complex life took a lot longer to happen. And so arguments could be made that complex life or life with brains and intelligence, because it takes so long to happen, because so many stages of evolution have to happen and so much time has to pass, it may be a less likely thing. And sometimes it may just take so long that the star dies before it happens, or life never evolves that far before it dies for other reasons of climate change and so on. So it's hard to be very confident that extraterrestrial intelligence exists because there are reasons to argue that it might be very rare, including the fact that we haven't found it yet and that all of our messages sent out into space have been unanswered, and we haven't detected messages from anyone else. Ready for the next question?
All right, so in the new astrobiology course, one of the activities is going to be calculating distances to stars and extrasolar planets. So this question from Uber Zeiska, sorry, I'm saying the last name very poorly, I'm sure, is related. Is it possible to calculate the distance between us and a star by analyzing the star's spectrum of electromagnetic radiation? And if so, how?
Stellar distance is actually one of the hardest things to measure. The first reason for that is that the direct method, which would be a geometric method, is only possible for stars that are fairly close. We do now finally have a satellite, Gaia, after falling on from the Hipparchus mission a few decades earlier, which is able to use the geometric method of parallax to actually measure the distances to now millions of stars. Until the Gaia mission, we only had distances for some tens of thousands of stars. And remember, there are 100 billion or a few hundred billion in the Milky Way. So it's obviously hard to measure star distances. Star sizes are also hard to measure because they're very small objects. An object like the sun, seen at a distance of a light year or so, 6 trillion miles, would look impossibly small. No way to resolve that with an optical telescope. So we can't see star sizes directly, and star distances are hard to measure. So, and also star masses are hard to measure. Unless the star is in a binary system, it's really quite difficult to get the mass of a star. You get a binary system and you can get it through Kepler's laws, but a single isolated star, you can't measure the mass. So to cut to the chase on the question, spectroscopy is a key in all of this work. And so astronomers can use spectra to measure the surface temperature of a star, and they can also use the spectra to measure the heavy element abundance or the chemistry of the star. And those two things are very helpful in placing a star in a context of evolution. And so it's really a model of stellar evolution based on all we know about stars and have learned in the last 100 years that allows astronomers to take a spectrum of some random distant star and with some confidence say that it's either a dwarf star or a giant star or a main sequence star, and with some confidence say what the mass and size of that star is. But it's based on a model. It's not usually based on direct observation. Ready for the next question?
Okay, the next question is from Jacob Olson, who's on with us live, who asks, how careful do we have to be when sending landers to various planets or moons in our solar system in order to make sure we aren't contaminating the surfaces with extremophiles that hitched rides with us?
Yeah, it's a big deal. And at NASA take it, I reassure people who worry about this, because it's worth worrying about, that NASA takes it very seriously. NASA takes planetary protection seriously in both directions. They obviously take seriously the possibility that if we bring a Mars probe back to the Earth or any space probe back to the Earth, probably a lunar probe is no danger. There's a danger of contaminating the Earth with an extraterrestrial microbe. That's a serious concern, and NASA takes enormous precautions over that. But in the other direction too, NASA has now pretty much a policy to do two things: to sterilize spacecraft as they approach and land on a planet, and to clean up after themselves as well as possible. The sterilization part is fairly easy for a planet like Mars, because although the atmosphere of Mars is thin, it's not that thin, and the heat shield in the spacecraft heats up enormously when going through the Martian atmosphere. And so because of the UV radiation of the deep space environment and this sort of autoclave heating of the spacecraft as it enters Mars, there's some confidence that really not much could survive entry to Mars and landing on Mars. The same may not be true of other destinations. Titan, for example, if we go back to Titan, there's a thin possibility there's some weird hydrocarbon form of life there. And obviously we wouldn't want to contaminate Titan with terrestrial microbes. But NASA does have methods basically that, of course, start before the spacecraft's launched to try and be sure that we're not bringing microbes to these foreign destinations. Ready for the next question?
All right, so I think this is going to end up being our last question for today, and it's from Aaliyah Hill, who's from Charlotte, North Carolina, who asks, What will be James Webb's main focus once it's launched? Will it be exoplanets or something else?
James Webb is finally on course for a 2021 launch. I think October is the date, and it really will hold to that because I think everything is fixed or on the way to being fixed. It's had some serious problems with instruments and bits falling off it during a shake test that got bad headlines a few months ago, large budget overruns, and so on. Congress was actually threatening to pull the plug on it for a while. It is going to go. It is going to happen. The technical hurdles seem to have been overcome. And when it goes up, it'll be up for the astronomy community to decide what it does its science on. Each of the instrument teams for James Webb have what's called a GTO, a Guaranteed Time Observation Program. So as a sort of reward for the enormous work and time of their careers that scientists put into developing instruments for space telescopes, they get some amount of time guaranteed to their science on the telescope. And it's a few hundred hours. It's quite significant. They get that data for their own exclusive use, but actually not forever. It all goes into a public archive at some point. Those scientists will, of course, look at all sorts of objects based on their research interest, and they tend to be broad. Many of those teams are going to be looking at young stars, galaxies, and some are going to be looking at exoplanets. The bulk of the time on the telescope is awarded through peer review. Panels of astronomers will judge proposals, and it is almost guaranteed that the amount of time requested on James Webb in its first few cycles, each cycle is a year typically, will be 10 or 15 or maybe even 20 times the amount of time available. So only 5 or 10% of the proposals submitted will get time. It's a really harsh selection process. Now, when that kind of process has been operated on Hubble Space Telescope over 3 decades, it sort of balances out that the Europeans get about the percentage of time they support the telescope for, which is 15%, and it sort of works out that the fields of astronomy get their fair due. Galaxies get about 40% of the time, stars 15%, planets 15%, cosmology 10 or so percent, and so on. James Webb has more particular capabilities as a telescope, and so its time will probably not be spread as thin as a multi-purpose observatory like Hubble. And it's almost certain that most of its effort will go in 3 directions. We'll go into understanding how stars form by looking deep into the nearest star-forming regions in great detail, by looking for first light of galaxies to see how the first galaxy light happened and when the first compact structures formed in the universe in the first few hundred million years, after the Big Bang. And the third will be exoplanets, in particular trying to do the very difficult spectroscopic work designed to sniff out biomarker gases in the atmospheres of Earth-like exoplanets. Those 3 fields will probably usurp most of the James Webb Space Telescope time for the first few cycles and will lead to some of the first spectacular results. Well, thanks for all your questions this week. That was fun. A lot of good black hole questions. Black holes will continue to be a topic, I'm sure, of interest for the audience here. And we'll try and get back to you in about 2 weeks.
All right. Thank you so much for joining us.
Thanks to the team for helping us. Thanks to the team for helping in Tucson and saying goodbye from London.
All right. This is Matthew and Grant in Tucson, and we're saying goodbye as well. So we'll see you next time. Take care.